Good morning, good afternoon, and good evening, everybody. Welcome to another edition of a Trillium Flow webinar. Today, we're going to discuss the design for changing duty conditions. Speakers today, there'll be myself, Barry Evans. I have a role in business development and I've worked in the pump industry for over 30 years. Dominantly with Weir Pumps in a variety of different front-end and operational roles, and now with Trillium Flow Technologies. Plus, I've spent 10 years working on subsea projects with FMC Technologies, with the role today working with the service team to expand operations in Europe, Middle East, and Africa. I'll hand over to Alessandro Nicco.
Good morning, good afternoon, and good evening, everyone. I am Alessandro Nicchio, and I am the after-sales engineering manager at Trillium Pumps Italy. I've been working in the pump industry since 2006, initially in R&D, focusing both in hydraulic and mechanical aspect of pump design, but now I'm taking care of all engineering aspects related to aftermarket, from troubleshooting to existing equipment improvement project. Over to you, Barry.
Okay. So before we go into the presentation itself, we'd like to introduce Trillium Flow Technologies and specifically the brand portfolio. The product brand names within Trillium Flow are synonymous with the pump and valve industries, with brands such as Begum Pumps, Flowway, Gabionetta, Rotojet, Wenco, and WSP, providing specialist equipment from hydrogritters, solids handling, through to high-speed barrel case pumps, more on that later, and high-volume concrete volute pumps. Also, on rotating equipment, we have a specialist team supporting steam turbines, backed by the Allen Steam Turbine brand. For our valve products, the brands are Atwood and Morrell, Bladeborough, Hopkins, Saracen, Sabine, all of these providing the valve product from control and choke valve applications through isolation valves and pressure safety valves, all leading names in the industry. More recently, our Redpoint product offering, and they provide critical duty, high quality valves with enhanced lead times to suit customer outages, including completion in exotic materials, depending on the process fluid and application. The Trillium Flow global presence provides opportunity for engagement and supply with major operating time zones, backed by our ever-expanding service network from Trillium service hubs, embedded service teams, and service partnering to support your operations. With this global presence, it provides us the opportunity to tailor technical and commercial packages of our products and service to suit all customers' project needs. Trillium Flow Technologies has got a long heritage, goes back over 190 years, and the corporation is now still adding products and services to make our customer processes more efficient and productive. I mentioned the company Redpoint Valves that joined Trillium Flow in 2020, which expanded the product and service provision for valves. And in 2022, we were joined by Termomeccanica Pompei, enhancing our expertise and offering in pumps for power, water, oil and gas, as well as enhancing the Trillium Flow Services portfolio. This provides the extensive network and knowledge base to service not just Trillium products, but equivalent product ranges from third-party providers, all with the confidence and reliability of an extensive service range backed by an original equipment design and manufacturing product platform. So going into today's discussion, it's focused on changing duty points as it applies to centrifugal pumps. Or more accurately, this can be explained as the difference between the design points applied for selection of the pumps at the conceptual stage and the ultimate demand which is placed on the pumps, or the process requirements and duty points dictated from the pump system itself. And this can happen, the changes can happen through a multitude of different scenarios, some of which we cover in the case studies provided, and Alessandro covers in his presentation in more depth as well. A frequent scenario results from how different disciplines approach arithmetic. So humor me a little bit if I share with you an analogy that I always have. If I ask an accountant or a banker to tell me the results of 1 + 1, he'll likely answer 2.00. Very, very concise. If I give the same question to a mathematician, most likely answer is 1.999 to infinity. But if I ask an engineer the answer, very quickly I'll get the answer 2, but he's going to add, let's make it 4 to be safe. And the result of that is often that the pump optimum duty selection is based on a requirement which has got a lot of contingency built into it. And this can then be different both at the initiation phase and through time. And that's before we take into account any system lifetime changes, upgrades, debottlenecking, expansions, variations in demand, and lifetime projections. Also, just want to add, if you've got any questions during the session, please put the questions in the Q&A section of the box, and we'll pick them up at the end of the session. And if we run out of time, we'll definitely send a reply if you give us your email. So if we go into the pump, what we're showing here is a typical HQ or head flow curve for a pump. And the selection of the pump from a pump company's perspective is optimized to ensure that there's a stable operation or a performance envelope for the given duty and includes an optimum and preferred operating range. Obviously, it's desirable for the operation to stay within the envelope and corresponding maximum efficiency points. However, for reasons previously suggested and system changes, this may not always be the case. The operating point of the pump after initial startup, this is a major topic in itself, the startup, but is the combination of the system static head or pressure combined with the dynamic system resistance as shown on this curve. So we've got the blue line is the pump head flow curve, the grey line represents the pump efficiency, and then we have added on here a system resistance curve for a normal pumping system. The intersection of the system curve and the pump performance curve shows the resulting pump operating point on the performance curve. For simplicity, we've assumed in this diagram single pump operation. There's other things to be taken into consideration for multiple pump operation. But this is represented by the intersection of the green and blue lines on the graph. If the system resistance is increased, say it's running higher, or there's a different calculation, then the pump is going to run back on its curve, and it will be outside the actual preferred operating point, still within the allowable operating curve. But you can see at this point, then the pump is running at a much lower efficiency. If the resistance curve is increased further, the pump will then run even further back and could move outside the operating, the design operating range of the unit concerned. The problem with that is, in extreme cases, as we can see from the red curve, that the pump is then operating in a very inefficient zone. Not just inefficient, there'll be recirculation in the pump, you'll get other effects, you'll get much higher vibration, and of course, the pump itself will not be running very efficiently at all. And as stated from the operator's perspective, operating outside the original specified preferred operating condition results in a lot of energy being lost in the system, but it results in increased downtime. And that is a consequence of the recirculation in the pump causing undesired mechanical effects and hydraulic effects in the pump, which can lead to premature failure, which is an early indication that the pump is not operating in the right position. So why do the conditions change? So from the previous slide, we can see the impact of the change for a given pump. And we kept it simple, not putting in too many multiple systems, but variations in the system resistance or the static head variations, changes in sea level, for example, or suction level, discharge levels, result in the pump operating in an area not originally intended. Many processes need a large degree of flexibility, and Alessandro will cover some of that in his presentation. And a lot of these conditions, although often anticipated at the outset, don't necessarily allow the changes in operation when you're in execution. And what I mean by that is that there may not been the expectation of such a variation. But from the example shown, we can see that a variation in the system resistance can have a significant impact on the operating point of the pump itself. So the system resistance determines where the pump will ultimately operate. But in these circumstances, we can work together with your own engineering teams to evaluate solutions such as a pump re-rate and variable speed. And we cover that within the presentation itself. So the options, which we're going to expand upon for the rotating equipment engineers, and that they'll be familiar with this, we go into details of the ways a duty point can be changed. We can divide the methods into two families. We have a dynamic method that aims to increase the operating region of the pumping system by adding more degree of freedom, the equipment speed, the number of pumps, the system curve itself. And then we've got static methods that include modification of the equipment to actually shift the design point of the pump itself. And of course, the main difference between the two families is the level of flexibility provided, or the level of flexibility required. The dynamic methods should be preferred when the process requires changes in duty point by design, while static methods should be used when process requirements are changed from original conditions, but are normally constant during pump operation. I'm going to hand over to Alessandro, and he'll go into this in a lot more depth. Alessandro, over to yourself.
Thank you, Barry. So let's start discussing the first and more common method to change a pump duty point, which is basically pump throttling. So nothing is modified, but the system curve is modified by acting on a valve. So as Barry was saying, there is an important concept we need to stress and underline. So the pump's operating point has to match the system head loss. So depending on the flow resistance provided by the system, so the sum of the friction in pipes, the head losses in filters, in valves, and so on, the flow through the system will be such that the head provided by the pump equals the head losses in the system, so that they can reach an equilibrium. And graphically, as Barry was saying, this is shown by the intersection of the system curve in red and the pump curve in blue. By throttling a valve, then the system head losses are increased, and by consequence, the flow through the pumps will be reduced so that the pump can deliver the higher head to compensate the increase of losses due to valve throttling. Conversely, opening a pump reduces the losses, and therefore the flow increases, and the pump develops less head so that the equilibrium is still maintained in the system. So while this is a very simple and effective way of controlling pump duty point, here comes the downside of it. So it's based on energy dissipation, so which is intrinsic, and it's intrinsically associated with an energy waste. So even though the energy is reduced, then the overall efficiency of the system is also reduced. So furthermore, while moving the flow far from the pump design flow rate, it exposed the unit to more wear and tear due to flow turbulences, potential cavitation, and increased the mechanical stresses in the pump, the axial load of the bearings, and above all, of course, the mechanical condition in which the pump is operating reduces the expected life of the pump. So in the next slide, we will see an alternative for this. Here we go. So here we have the picture is now showing, so from the initial curve, the red curve, the system curve on the right, while we are throttling the valve, the curve gets steeper so that the intersection will move on the left side, and the delta, the difference, is associated with the energy which is actually dissipated. So to avoid that, what we can do is to increase the level of flexibility of the system, just like it's shown in the next slide. So varying the pump speed is actually a great way to adjust the pump output to system requirement. So pump speed change is much more effective as the flow head and absorber power of the pump are decreased by slowing down the pump, and vice versa, they are increased by accelerating the unit. So what the picture is showing on the right side is basically a family of pump curve at different speed that you can see they intersect the system curve shown in black at different flow rates. So the idea is to select a certain speed to match the actual desired output of the pump without any need of dissipating an excess of head provided by the pump, just like it was happening with pump throttling. And in either condition, the pump can be selected to operate at best efficiency point, and it is maintained even though the pump speed is changing. So we can keep the efficiency at the maximum. And this not only reduces the absorbed power and keep the efficiency high, but it also reduces the mechanical stresses and therefore the wear and tear of the pump component. As a consequence, the pump life is longer, mean time between failure is increased, and the cost of spares and energy, of course, is reduced. Now, when the process requirements are very diverse, the best way to handle such variation is to change the number of pumps that can operate in series, just like in the bottom of the slide, or in parallel, just like in the top part of the image, to increase flow rate. So pump operating in parallel, as an example, is a very common way of coping with very diverse flow rate, especially in fluid transfer services and in pipelines. It's important to note that the change in pumping system output in these cases can occur only at fixed step, as we are switching on and off a discrete number of pumps. And very often this control method is then combined to to valve throttling or speed adjusting to achieve a more fine change in duty point. One of the main advantages of having more than one pump in operation and installed is that it provides a contingency and increases the system reliability, because even if one of the unit may not be able to operate, there will be in any case some kind of output from the remaining available unit, both in terms of head and flow out of the system. We will now deal with static methods to change the performances, and specifically we are now addressing what we can do inside the pump, so some modification to the equipment, specifically to the rotating equipment, to the rotating parts, of the pump to change its performance. The first way is, in fact, to replace the impellers with other impellers having a different design and therefore different performances, or to modify the existing impeller to optimize the pump output. For example, impeller trimming. So a rotor change is, of course, less expensive compared to a complete new unit, and this allows switching back to previous operation if we keep the original parts available. Rotor redesign is also a great opportunity to increase overall efficiency in absolute terms and to reduce the stresses due to mismatching of performances. For example, first stages can be improved in terms of MPSH if one of the conditions that has been changed by process changes is also the MPSH available. Furthermore, the time required to change the duty points can be compressed when replacement kits are organized. For example, when a complete BB5 cartridge is supplied as a retrofit kit, or with OH2 back pull-out assemblies, or simply when we are replacing entire rotors for BB1 or BB3 pumps. In the next slide, please, Barry. So with the increasing of magnitude of the duty point change, modification of the rotor pump may not be enough, and there is need to act also on stationary parts of the pump, which is the casing and the volute, to achieve the target. As an example, the casing volute can be modified, enlarging the throat areas, for example, to increase the maximum flow achievable. So we can increase the passages of the stationary parts of the pump to obtain a shift to the right side in the flow head curve of the best efficiency point, therefore allow more flow to be elaborated by the pump. So as a rule of thumb, intervention on stationary pump is normally required when the change is greater than 25-30% of the best efficiency point flow rate. But of course, in all cases of duty point change, it should be considered associated to rotor changes, because it makes much more effective, and it allows for a better and deeper optimization of the pump performances compared just to a change in the rotating part only. Also, in this case, the pump operating conditions are improved, and there is the possibility to alleviate mechanical stresses, again, resulting in significant savings in maintenance and spare parts requirements for the unit. For very big units and very high flow rate, as a rule of thumb, again, in the region of 10,000s of cubic meters per hour. So units are generally designed with that have an axial flow design. Impeller can be designed with the possibility to change blade angles. And changing the blade angles will modify the pump performance output. So the image on the right side, the pump performance curve, again shows different performance output with different at different angles of the blades of the same impeller. So depending on the type of the mechanism which is used to adjust the blade angle, this variation of angle can be done with the pump installed at site without any dismantling activities, or it may be required to open the pump and readjust the vanes at a service center. So while this method is basically available just for quite rare units or a very big pump, this is extremely important because such units can suffer a lot of mismatch of operation between the actual condition and the design condition. So having one of these units operating far from its best efficiency point can result in severe vortex, circulation phenomena, mechanical troubles, and the reliability of the unit can be heavily jeopardized. So it's very, very important. So I'll hand over back to Barry to illustrate a real example now of case studies for duty point changes.
Thanks, Alessandro. The first case study is in the category of a static intervention and considers changes that can be effected within the pump itself. For this case study, we were dealing with a BB5 multi-stage barrel casing pump, and the oil field reservoir, which was an offshore platform, the output had declined from the reservoir itself since the original platform design. The capacity was established, such that the pump had to be throttled back to match the system output and balance the system. With our experience as pump original equipment solution provider, we could consider all options, both dynamic and static, together with the operator's own engineering team. However, because it was an existing offshore platform, there were physical limitations which ruled out variable speed drive system. And so the solution investigation focused on options to change the hydraulic performance of the unit within the physical envelope of the cartridge and barrel itself. With this style of pump, this provided options for changes with the removable cartridge. With other styles of pumps, that might be the actual rotating element, but this one, the entire cartridge can be changed out. And the solution team focused on what could be achieved with the hydraulics of the cartridge to match the operating demand of the system for a lower flow and lower total head. By designing the new cartridge, or the hydraulic bundle of components, to achieve a re-rated cartridge, the actual design of the unit lent itself to the re-rate situation. And it's not limited to multi-stage barrel pumps. Most pump rotors and hydraulics can be evaluated, as Alessandro pointed out, with a previous single-stage pump. And our solution team provided the support with both Trillium Flow hydraulics and third-party manufacturers. First, I think just a quick comment, because we use the term re-rate and it might cause a bit of confusion. So the re-rate is where the pump hydraulic performance is moved from the original design condition of the pump selected, and it provides a completely different profile, and it's intended to move the overall operational best efficiency point, whilst keeping within the physical boundaries of the existing unit. The re-rate changes the hydraulic characteristics themselves. Destaging and adopting different impeller cut or vane profile, or a combination of all three of these, can provide a different hydraulic performance curve profile. The hydraulic profile can be steepened or adjusted to move the best efficiency point closer to the desired or the new duty point, which is the result of changes in operation. At the same time, ensuring that we get a stable characteristic is adopted within the operating range of the pump. The key, I suppose, is when or what causes or triggers a re-rate consideration. The most obvious is when there's a process change implemented somewhere else in the system. The actual demand conditions will move significantly from the original design. That's what we encountered in this case study. But it could be a combination of factors that trigger the re-rate. There could be energy cost changes in terms of the output, or rather the input power, not relating directly to the net output delivery of the pump. Or it could be a decrease in reliability. Alessandro touched on that. The mean time between failures might decrease, and there's higher energy costs as an experience of more intervention with the pump units. So as indicated in the slide, an oversizing of the original design condition itself could trigger the re-rate. This is where our solution teams, the operational contract management team, if they're engaged, can work with the customer's own, with your own engineering teams to evaluate each of the above conditions to determine an optimum solution. For the case study in question I mentioned earlier is that we engineered a completely new cartridge, and this ensured that the hydraulic bundle of the impellers and diffusers was optimized for the revised operating condition. We prepared a mechanical design ensuring the revised unit meets the revised duty condition using original equipment design guidelines and principles. Thus, the new cartridge will operate optimally both hydraulically and mechanically at the revised duty point. The advantage is the replacement cartridge can be manufactured separately, prepared for installation in a planned intervention, and change out of the cartridge on the platform. And that's what happened on this UK North Sea application. Most of the work was done off the platform, which was the cartridge was then shipped out, and our team was there together with the client's own installation team to complete the change out. The target in the case study was to achieve an optimum flow at 65% of the original design. And this was due to the reduced export rates, which meant that the generated head itself was 12% lower than the original design, due to the reduction in the system resistance. However, the requirements were that the existing barrel casing and pipework, plus existing fixed-speed motor, were to be retained. So we can see from the slide that the requirements that they're depicted on the pump performance curve on the right was quite considerable derating. The derated condition is in the green. And the options for changing the pump impeller, diffuser, and hydraulic passages whilst maintaining the original speed and physical envelope of the installed barrel. The team carried out an evaluation of both the hydraulic design as well as mechanical design of the revised cartridge. The hydraulics using computational fluid dynamic checks, and mechanically including a rotor dynamic study to ensure that there were no undesirable operating conditions introduced by the change in the new cartridge. The final solution included a performance test of the hydraulic bundle within the cartridge in a test barrel. And we were able to do that in one of our manufacturing facilities, together with the client's engineers, to demonstrate the capability of the new cartridge before it was deployed offshore. This ensured the unit would provide the required duty conditions when deployed offshore without introducing any undesirable effects that can take place when you're moving a duty point significantly. So if I sum up on the slide, the results of the re-rate from the case study to match the new duty flow rate. In this case, the pump best efficiency flow is now running at 94.3%. It's 94.3% of the best efficiency point, compared to running it, the throttling back, at the point where it was at 36% in the original hydraulics, which is well outside the desired operating range. And significantly, the operating of the efficiency at the duty point was moved from 57% to 70.7%, as can be demonstrated by the actual absorbed power, which was reduced from 2,950 to 1,750 kilowatts with the derated cartridge. And that realized a saving in operating costs purely through the power of $2.4 million per year, way paying for the change out of the barrel in the first year. And that's without taking into account the saving in service and operational running costs from the interventions that would take place with running the pump outside its desired operating envelope. And we've also included on the slide, and this day and age, it's critical to look at the net saving of 4,400 tons of carbon dioxide per year. So I'm going to hand back to Alessandro, who'll cover another specific case study that we undertook.
Okay, so thank you, Barry. This one is handled with a modification of a unit dealing with a transformation from a fixed speed unit to a variable speed unit. So the next, here it is. So this is the image is showing a typical skid of a unit operating at fixed speed. So we can recognize a pump, in this case, a BB5 type pump, a motor. And of course, if there is nothing in between and there is no variable frequency driver to change the frequency of the motor, the unit is designed to operate as a fixed and constant speed, therefore provided a kind of a constant output. But unfortunately, the reality of the plant in which this unit was designed to operate, the plant demand was widely different, showing all the typical characteristics of a dynamic system requirement. So fluctuation of plant demand with operation out of the pump preferred operating region, far from the best efficiency point, seasonality of the requirements, and the necessity of wide throttling with consequent energy dissipation. So Trillium proposal to the end user was to increase the flexibility of the pumping system by installing a variable speed coupling so that the pump speed can be adjusted to cope with plant demand. These modifications, of course, were intended to maximize the efficiency of the pumping system, reducing the energy of waste, improving the pump working condition, and reducing the cost of the absorbed power of the unit. So in order to be effective and efficient, this modification needs to be carefully evaluated and planned before the execution, considering not only the pump, but the whole system in which the pump is operating. So the first step is, in fact, an audit on the existing operating condition with an initial assessment of pump performances based on the data available from DCS. Then Trillium Field Service Engineer visited the plant to conduct a site survey to complete the data collection over the pump performance, so going in more details, sitting side by side with the operation team of the end user, but also to acknowledge and take into consideration all the constraints of the installation at site. Once these complete pictures of the unit and the operational parameters were available, it was possible to conduct and complete an analysis to determine the new design conditions that have to be achieved with the modification in order to achieve the desired flexibility and new pump efficiency over the entire range of operating points. So once these requirements are set, potential solutions are determined, and then it was time for our engineers to complete the feasibility study of the modification and to validate these modification. So in the specific case, as we are dealing with a change in speed, so the feasibility checks, of course, include hydraulic performance check, so to ensure that the new operating condition can be reached within the speed range that the variable speed coupling was able to provide. And then, but also, of course, we had to consider all the rotodynamic aspects. So being a multi-stage pump, it's of paramount importance to avoid resonances and that are affected by the pump speed. Therefore, the design of the rotor have to be verified so that the reliability of the pump is maintained. The next step comprises, of course, the fabrication, the supply of all the parts required for the modification, and the implementation at site. Last but not least, the modified units were tested with the support of our field service engineer to validate the achievement of this project. So here on the right side of the picture, how it looked like. So the skid after the modification has the variable speed coupling in between the pump and the motor, shown in blue. And what we had to consider as we were dealing with a modification of the complete skid, we also take care of all the ancillary equipment. In this case, for example, the heat exchanger to cool down the oil used by the fluid coupling in green. So this is to provide, of course, to the customer a turnkey solution which is addressing all the aspects of this modification. The next slide shows the real pictures of the installation at site, where again it's clearly visible the variable speed coupling in between the motor and the pump, as well as the modification in the piping system for the cooling down of the oil. So the typical scope of work of such a project, of course, include then the study and the design of the new skid, all the relevant technical documentation, update and engineering studies. So the drawings for the general arrangement drawings, all the documents and quality plan for the variable speed coupling, eventual instrumentation installed. All these aspects are covered. Of course, the scope of work includes the supply of material, which is required for the modification, but also the manpower to implement this. So the field engineer and supervisor as required in the different phases of the project, with the execution of all the activities aside, including the testing and commissioning. And of course, the benefits for the end user. So the benefits achieved by this energy saving project are listed in the slide, and it was possible to modify the existing unit with minor impact over the existing installation, avoiding modification of pipe, electric system, and motor that remains the same. The unit is far more flexible and capable to adapt to plant demand, keeping a higher level of reliability, with a minor complexity added to the system. So there were no changes to be implemented in the DCS system. And of course, the operating condition for the pump are now, thanks to the variable speed coupling, less severe, resulting in a lower wear and lower stresses for the equipment. And most important of all, the system efficiency was largely increased, and therefore the cost of energy strongly reduced. So these were the three main stream of benefit for our end users. Finally, we are going to summarize what we have discussed so far in this webinar. So rated operating conditions are often different from design condition, and this always comes with a waste of energy and worsening of pump operating condition. So there are two main reasons for a duty point change. What we have defined as static changes that occurs when new pump duty point is required by the process. That is a change at a certain point in pump life, or simply when incorrect pump rated point was specified at the design stages, very often, as Barry was saying, just because of excessive wide margin overhead requirement. Then we have dynamic changes, that is when the process in itself needs flexibility by design. So there are different operating conditions that have to be achieved by the unit. So the unit has to operate at multiple points. Luckily, there are many solutions to improve the situation in both cases, but this has to be evaluated on a case-by-case basis. So the most common solution available are the re-rate, the transformation to a variable speed thanks to a variable frequency driver or a variable speed coupling. Then we have the modification to the rotor or the combined modification of rotor and casing, but many others are available, again, depending on each specific case. It's important to underline that the collaboration between us, the service provider, and the end user, it's really critical to success. And we have learned from our experience that the whole system shall be included in the analysis. So we get the best out of this project when not only the pump is considered, but we, thanks to our knowledge and expertise, we can give a look to the pump operating into the system. Most important of all, then we need to remember why all these is important. All the best practice we have described so far will lead to significant savings from the end user, so from an OpEx perspective. And last but not least, this will increase the environmental sustainability of the pumping process, which is a topic today always more and more important. Now the presentation is completed and we can open our Q&A session. So if you haven't done so, you can add a question to the tab at the bottom of your Zoom view. So there are a lot of questions in. We may not be able to reply to all because of time constraint. We will follow up by replying by email. So the first question, can impeller trim reduce drastically the overall pump efficiency? And is it often required an increase in impeller due to the increased system resistance caused by fouling? So, of course, there is a relationship between the impeller trim and the efficiency, and the reply is yes. If you cut the impeller, the efficiency is normally reduced. The point is, the reduction in efficiency due to impeller trimming is usually far less than the energy waste you are causing by throttling the head with the valve. So trimming the impeller will allow the pump to generate less head and allow opening of the valve. And the overall balance of energy is usually in advantage for the impeller trimming. So the effect at the end after the valve is the same, so less head is generated. The point is that by impeller trimming, the head is not generated by the pump and the power is not absorbed by the motor. With the valve throttling, the head is, so the power is absorbed, the head is generated and then dissipated into the valve. So hopefully this replied to the impeller. Another question for you, Barry. What's the typical lead time for a re-rate project?
The re-rate project would itself dominantly take place in parallel whilst the pump was still operating. So that could be anything from 6 to 8 months. When it goes off-site to the platform, then that would be a period of maybe 2 to 8 weeks for the implementation in the platform. But the pump is still kept running whilst that's taking place. There was another question came up just now for the UK North Sea case study, was about the variable speed drive and why wasn't there a variable speed drive fitted? And the reason is there was no space available on the platform itself. We had to keep the physical limitations of the existing control gear so that the focus turned to the pump itself. And of course, if you start changing any significant weights on a platform, it does affect the original design case. By focusing on the pump, it meant that some of the other parameters didn't have to be addressed in an engineering change management application. Alessandro, back to you.
Yeah, I think that this last reply also replies to another question, which is asking why, if the supply of a new pump was considered instead of this rate, just because, I mean, that's a matter of keeping the same constraints. So yes, there may be the possibility to have a smaller unit, but in the matter of fact, it means rerouting of piping and a lot of additional constraint that may not be even economic or allowed when you are operating on a platform. So,
and of course, that would have been considered as part of the evaluation, the selection of a new pump. But in fact, at the end of the day, there's advantages on both sides, as the person who raised the question covers. But at the end of the day, working with the customer's engineers, they chose, and it would be the most economic solution. I've certainly found in dealing with any offshore platform, they're very conscious of cost.
Exactly. Then most of the question asks for specific cases or what is possible to do. So a general reply would be, so there are a huge variety of solutions available. And the important thing is to understand that every case is different and we need to operate, to cooperate and co-engineer the solution from ourselves, the service provider, and the end user. So there is no unique question or a unique answer to every specific problems, but every situation has to be analyzed on a case by case, as definitely we can provide a solution addressing specific boundary condition to each problem. So as a general advice, if you feel you have if one of your operating pump falls into one of these categories, so reach us, talk with us, show your numbers, your data available, and for sure there is some solution we can draft together, considering the peculiarity of each installation, of each service.
I think we're on the air now for the webinar. We thank everybody for your time, taking time out your schedules. We know how difficult that is.
And thank you again for joining the webinar.
Thank you.